I'm Kenny.
I'm Richard.
I'm Riley.
I'm Jay.
And we're gonna present our radar. So the objective of the radar is to kind of design all your components. So you have to like block diagram of your radar. You have to design all the components using the components that are given, like sounding boards, and test the components, test the systems, finalize the system, put some software in it, test it, like test the overall radar, make sure it works, then start implementing some upper level stuff like phase lock loop, and that's about it. You start tuning it a little bit more, and then you're good. So hopefully we should have all gotten there, but we didn't. We made it to about halfway through systems testing, so we kind of got it going, and it didn't really work too well. We had all the components hooked up to the mixer and trying to read outputs of the mixer and see if our radar was working, if at all, and it was not. And so instead of just telling you guys about our radar and like the future implementation we had, we're going to talk more about troubleshooting and kind of like the tips that we found that were really helpful. And hopefully this can be used for like, third years that haven't taken 335 yet, so they know what's happening.
Alright, so to define our radar, there was optimize, which is the ideal operating of everyone's radar, and hopefully if you got it to work, that's where it would be. And then for us, there was getting by, which is where all of our components landed, or at least most of them. The component that gave us the most trouble and pretty much set the standard for getting by was the antenna. Just because knowing how we're supposed to ideally operate within the 2.4 to 2.5 gigahertz range, when we built our antenna, it was actually lower to 2.35 to 2.365 gigahertz. And so that pretty much went and said, all right, this is where all your components are going to need to be at. Following that, our getting by, which was not really getting by either, because it was the amplifier, which pretty much halted the building of our system because our amplifiers were not giving out enough output.
So to start things off, we had our components out, and we would troubleshoot the components, and you would have your ideal of gain and loss, and then you would have your getting by gain and loss. And sometimes we just screwed up somewhere in building components and it just didn't work. So there's a lot of troubleshooting around that, and we tried a lot to bring it up to standards. So let's start with the amplifiers. You have this gave us the most trouble by far, and kind of really set back the project. So we started with the 3+, and that, you guys all know on the data sheets at around 2 gigahertz, it's like 18 dBs a gain, 15 is fine. I don't know anyone that got up above like 17. I don't remember, but ours we had around 12 and 13. Yeah, cool. So we got to about like 12 and 13. Something has happened. We tested it some more. It broke. We had to use the EE541, which like ideally has already like about 6 dBs a gain lower than the 3+. And with the way we were building our components, it just had terrible gain at like 6 to 7 on one, and 8.5 plus, 8.5 to 9 dBs a gain on the other. So there's a lot of issues with that. Here's just data. It's kind of nice, real pretty. And so what we determined what was going to be the problem with our amplifiers was there were probably air gaps, like at the bypass capacitor to the ERA, there's air gaps, poor connection, poor SMA like build quality. So there's not going to be a whole lot of it's not going to be a very clean path, and the math might have gone wrong for like the RF choke or the DC resistors and whatnot, and through-hole components might not be the best choice. So there's a couple issues.
Oh, okay. So for the splitter, we were also having problems with that. Our first iteration of it, we used through-hole components for that, and it worked, but we were getting about -12 dB drop, so it wasn't. It was definitely not going to get us by. So we switched to the SMT resistors, and that in itself created a huge problem. And just trying to solder those joints, we had the problem where we had some air gaps in there, so we weren't having continuity on one side, so we were getting like a negative 10, negative what?
24.
24 dB drop on one side. So when we fixed that, we ended up getting approximately like a negative 6.35 dB drop, which is what we wanted. So after all the troubleshooting and going on with that, we eventually got what we wanted. Optimal, like it says on there, is -6, and we got pretty close to what we wanted. So the splitter was definitely not a huge problem like the other components that we had.
VCO characteristics. This is just,
continuity on one side, so we were getting like a negative 10, negative what?
24.
24 dB drop on one side. So when we fixed that, we ended up getting approximately like a negative 6.35 dB drop, which is what we wanted. So after all the troubleshooting and going on with that, we eventually got what we wanted. Optimal, like it says on there, is -6, and we got pretty close to what we wanted. So the splitter was definitely not a huge problem like the other components that we had.
VCO characteristics. This is just, the VCO was a chip that we just kind of set up by hooking up just a power supply and one of the Rigels with a ramp. And this was fairly close. I mean, there wasn't too much. It was already built. That was really nice.
So most of the testing for the VCO was pretty much to fit the ratings of our radar, since they were going to be performing between the 2.35, 2.36 range instead of that 2.4, 2.5 gigahertz range. And so we were just working around the different different types of inputs to kind of see what is going to give us that required output within that range. And then next is our mixer. You can see what we actually got compared to what was desired was pretty similar in terms of gain. We just attribute that to the fact that the mixer, compared to the other things like the tiny resistors and amplifiers, it was just a simpler process in terms of putting it together, because it was just a single chip and attaching those leads together. And it's just a capture of our testing of the mixer. So these are the few issues that were there with the mixers. It's just really being careful with that air gap being produced when connecting those coaxes to the mixer itself.
Okay, so another thing, like he was stated before, was when we were tuning our antenna, the first problem that we had was when we were testing it in the chamber over there, cutting the wire to the right length that we wanted to get that 2.4 to 2.5 gigahertz range was a little difficult. Our first go at it, we cut it a little too far, so we weren't getting it anywhere near that. So we had to take that SMA cable out and put a new one in and recut. But once we did get it to an optimal range, we were getting about a pretty big gain on there, like a negative, or was it negative 30 or 30? It was something pretty big.
Very significant, just not at the frequency range we wanted.
Right, so that's why when we designed all the rest of our components, it was around a 2.35 to 2.365 range. So other than that, there weren't really any big problems with the antenna, other than just getting the proper spacing from the back wall. That was real important that we found out, that lambda over 4. Other than that, the antenna was another easier component that we created.
So with all that said, after we tested all the characteristics of our components, there are some full system tests that we implemented in order to fully test the viability of our radar system. So here's subsystem test 1. Here we're testing the power output coming from our second amplifier from the splitter. And as you can see, most of the data seen is going to be fairly similar to all those other subsystem tests, and we figured out is that the amplifier is not amplifying enough gain in order to really have that output port from the splitter to detect that detect any signal or reflection coming off of the antenna. So from our frequency range, we're only outputting 7.01 to 7.74, which we should ideally be outputting around 10 dB.
So for this test, we just did a through line test to see whether or not how much power was coming out of the second amplifier. It was much more simpler. It was simpler than just using 2 antennas, and we didn't have to worry that much about noise. We used about a 30-foot cable, so there's some loss within that. That was better than our antenna, so we could actually see whether or not our system would be working. And this was just to see whether or not we could actually get the gain. It's just like a proof of concept.
And just to kind of continue that proof of concept test.
Hi, I'm Kenny, and this is 541. 541, where we present our radar.
I'm Richard. I'm Riley.
So here we have our input to our voltage controlled oscillator, which is a ramp function from 6.5 volts to 6.7 volts. This will give us a frequency between 2.35 and 2.37 gigahertz, which is in the range that we want for our frequency, for our antennas. Over here, we have 2 different voltage sources, and this is for the voltage controlled oscillator, and this is for the amplifiers. One requires 8 volts, the VCO, and the amplifiers require 12. Therefore, they have to be separate from each other. And moving on, we can see this is our transmitter side, where it goes from VCO to splitter to amplifier and to our antenna, which transmits. And the splitter will split from transmitting down to the frequency mixer, which we can get to, which is our receiving end. So you have the frequency mixer and the amplifier and the receiving antenna. So our input will be the receiver, it will go through the amplifier to give it some gain, and it will be mixed from the LO coming from our VCO and whatever our RF is to give us an output to read as our IF on the spectrum analyzer.
So the testing setup we have are the 2 antennas acting as a radar and a moving piece of metal to pick up the sent out frequency and picked up by the receiving antenna. So the frequency range that we have is 2.35 to 2.36 gigahertz, which gives us a bandwidth of approximately 10 megahertz, which we'll be measuring on the spectrum analyzer. So the spectrum analyzer is spanning from a frequency of 0 hertz to 12 megahertz, and that's because the bandwidth of our system is at approximately 10 megahertz. So any signal that comes from the piece of metal to the receiving antenna will be picked up at approximately 10 megahertz. Right now, the frequency from the VCO is at approximately 100 hertz. So right now, we're just getting the noise spikes from it as we move the piece of metal towards the antennas. Now, as we change the VCO frequency to 1 kilohertz, we can see that the noise spikes are more frequent because of the harmonics of the 1 kilohertz wave. And this just proves the point that our amplifiers aren't amplifying enough to receive a signal that's above the noise level. So this is the biggest reason why we aren't able to pick up any signals from the moving piece of metal or any object in our testing.